Have you ever found yourself staring at a complex scientific text, maybe a dense chapter from an advanced organic chemistry book, and felt that familiar wave of overwhelm?
Oh, definitely. Molecules seem to dance in a secret language, and yeah, the sheer volume of information can be really daunting.
Well, you are absolutely not alone, and that's exactly why we created the deep dive.
We're here to be your ultimate shortcut to truly being well-informed. We take that complex source material, stacks of articles, research, expert notes, and distill them into the most important, insightful nuggets.
Think of it as your custom-tailored journey, designed for you, the curious learner, to transform that information overload into genuine aha moments.
Exactly.
And today we are taking a deep dive into one of the absolute cornerstones of organic chemistry, nucleophilic substitution.
We're drawing from one of the most respected texts in the field, delving into its core structures, reaction mechanisms, and the surprising ways these fundamental principles play out.
Yeah, this isn't just about how chemicals swap partners.
Yeah.
It's about the essential reactions that underpin countless processes, from creating life-saving drugs in the lab.
To the massive industrial scale of petroleum refining that literally powers our world. It's huge.
It really is.
That's right. Nucleophilic substitution at carbon atoms is a concept that organic chemists have been studying and refining for nearly a century now, ever since the foundational work of C.K. Ingold and E.D. Hughes back in the 1930s.
Wow, nearly a century.
Yeah, it's a perfect illustration of how these broad foundational concepts give us a framework, to understand what to generally expect. But it's the finer details, the subtle nuances that truly reveal the distinctive and often surprising aspects characteristic of a specific chemical system.
Okay, so let's unpack this crucial area. So when we talk about organic reactions, it's not just about what you start with and what you end up with, right?
Not at all. It's fundamentally about how the reaction happens, the precise pathway, what we call the mechanism.
And early on, Hughes and Ingold defined two crucial limiting cases for nucleophilic substitution, kind of like poles on a spectrum, the SN1 and the SN2 mechanisms.
Exactly. Shall we start with SN1? The ionization mechanism. It's really a tale of two distinct stages.
Let's do it.
Okay, so what's truly fascinating about the SN1 mechanism is how it kicks off. The first step is slow, often difficult, like a chemical divorce.
Huh. A chemical divorce. I like that.
Yeah. The reactant, Rx, undergoes what we call heterolytic dissociation. Basically, the bond breaks unevenly.
Unevenly how?
Well, the leaving group, X, takes both electrons from the bond. This leaves behind a positively charged tricoordinate carbocation, essentially, a carbon atom with only 3 bonds and an empty orbital.
Right, positively charged.
And a negatively charged anion, the leaving group. And this carbocation, crucially, is typically planar sf(p)2 hybridized. That geometry is key.
Okay, and that first step, that bond breaking, that's the slow part, right?
Oh.
The bottleneck.
Absolutely. That's the rate determining step. Once that carbocation is formed, though, everything speeds right up. The second step is incredibly fast.
So the remarriage is quick.
Exactly. The newly formed, highly electron-deficient carbocation rapidly combines with any available electron-rich species, a nucleophile, that's hanging around in the reaction.
And that forms the final product. So slow divorce, fast remarriage.
You got it. A two-stage process.
And this two-step nature has big consequences for the reaction rate, the kinetics.
Profound implications. The overall rate of the reaction depends only on the concentration of that initial reactant, the Rx. We write the rate law as rate equals K1Rx.
So that's why it's called unimolecular, just one molecule involved in that slow step.
Precisely. And critically, the concentration or even the identity of the nucleophile doesn't influence how fast this initial slow bond-breaking step occurs. It's just not involved yet.
If you were to visualize this on an energy diagram, what would it look like?
You'd see two distinct humps, energy barriers. The first hump is higher, that represents the energy needed for that slow ionization step. This leads down into a valley.
The carbocation intermediate.
Exactly. The carbocation sits in that energy valley. Then there's a second, much smaller hump, representing the low energy barrier for the fast reaction with the nucleophile to form the product.
And that first step, the tough one, is endothermic. Needs energy.
Yes, it requires energy input. And the transition state for that first step, the very peak of that first hump, strongly resembles the carbocation product that's about to form. It's already developing that positive charge in planar geometry.
Okay, so what factors actually make this SN1 reaction go faster or slower?
Several crucial factors. First and foremost is the stability of that carbocation intermediate.
Makes sense. Easier to get over the hump if the valley is lower, more stable.
Exactly. The more stable the carbocation that forms, the faster that initial ionization step proceeds.
And how do you stabilize a carbocation?
Primarily through electron donation from surrounding groups. Alkyl substituents are good at this through hyperconjugation, which we'll get into. Also resonance, if you have adjacent double bonds or aromatic rings that can spread out, delocalize that positive charge.
Okay, stability is key. What else?
Second, the leaving group's ability. It's paramount. A good leaving group needs to be able to comfortably accommodate that electron pair it takes with it when it leaves.
So it needs to be stable on its own.
Precisely. Typically, it's a stable anion, like iodide or bromide, or a neutral molecule like water. Basically, something that's happy to leave and unlikely to come right back.
Got it. Carbocation stability, leaving group ability. What about the surroundings? The solvent.
Oh, the solvent plays a huge role. Almost like a helpful matchmaker or maybe a mediator in our divorce analogy.
How so?
Polar solvents are fantastic at stabilizing the charge separation that develops in that critical transition state for ionization. They essentially wrap around the developing positive charge on the carbon and the negative charge on the leaving group.
So they lower the energy of that transition state, make the hump smaller.
Exactly. They make the ionization easier and faster. You can picture the solvent molecules, like tiny helpers, surrounding and stabilizing those separating charges, making the whole divorce much smoother.
Interesting. Is there a flip side?
There is, actually. It's subtle. If you start with a reactant that is already positively charged, like, say, a trialkyl sulfonium ion.
Okay, starting with a positive charge.
Right. In this case, ionization leads to charge dispersal. The positive charge gets spread out over the carbocation and the neutral leaving group. And here, surprisingly, polar solvents might actually moderately slow down the reaction.
Why would they slow it down?
Because they stabilize the more concentrated charge of the initial reactant more effectively than they stabilize the more diffuse charge spread out in the transition state.
Yeah.
It's a bit counterintuitive.
Huh. Okay, and what about steric effects? Just, bulkiness.
Also a bit counterintuitive for SN1. Well, you might think crowding always slows things down. Steric compression in the initial reactant can actually favor ionization. How?
As the molecule transitions from a crowded tetrahedral reactant towards a more spread out planar carbocation, it relieves some of that internal strain. It can breathe easier, so to speak.
So becoming planar relieves crowding.
Often, yes. This makes the ionization step energetically more favorable, effectively pushing the molecule towards forming that carbocation. However, if the molecule's structure, maybe a rigid cage, prevents it from becoming planar, then the energy needed for ionization skyrockets and the SN1 reaction basically stops.
Fascinating. Okay, let's move to stereochemistry. This is where things get even more interesting with SN1, right? The whole racemization puzzle.
Absolutely. As we said, the carbocation intermediate is sp2 hybridized and planar. In an ideal world, if this carbocation lives long enough and fully diffuses away from the leaving group,
Well, it gets where it came from.
it becomes symmetrically surrounded by solvent molecules. In that perfect scenario, the nucleophile can attack from either face the top or the bottom with equal probability.
Leading to a 50.50 mix of mirror image products. Exactly. A racemic mixture. That's the classic SN1 stereochemical outcome.
But I sense a but coming.
There's always a but in organic chemistry. Often you don't get a simple, perfect racemic mix. This observation led to the crucial concept of ion pairs, introduced brilliantly by Saul Winstein.
Ion pairs. Okay, what are those?
Winstein proposed that the carbocation and the leaving group don't always immediately split up into completely free, independent ions swimming around. Instead, they can remain associated in distinct stages.
Stages, like what?
First, you might have a contact ion pair or intimate ion pair. Here, the cation and anion are still right next to each other, intimately associated.
Okay, still touching, basically.
Pretty much. Then, solvent molecules can start to slip in between them, forming a solvent-separated ion pair. The ions are still together due to electrostatic attraction, but they have solvent molecules acting as a buffer or cushion between them.
So a bit more separation.
A bit more, yes. And only after these stages do the ions fully dissociate and become completely independent, symmetrically solvated species free to roam.
Wow. So ionization isn't just one event. It's a journey through these pair types. How does this affect the stereochemistry?
This is the key insight. Nucleophilic attack can happen at any of these stages, and where it happens dictates the outcome.
Okay, walk me through it.
If the nucleophile attacks while it's still a contact ion pair, the leaving group can physically or electrostatically shield one face of that planar carbocation.
Blocking one side.
Effectively, yes. This often leads to attack from the opposite side, resulting in a net inversion of configuration, kind of like you'd expect in an SN2 reaction, even though it went through a carbocation.
Whoa. Okay, what about the solvent-separated pair?
Here, there's more flexibility. The nucleophile has a better chance of approaching from either face, but the leaving group, or even the surrounding solvent molecules, might still subtly bias the attack direction. This often leads to partial inversion or maybe even some partial retention. It's less predictable.
And finally, the fully dissociated ions.
That's where you get the classic outcome. A completely dissociated and symmetrically solvated carbocation will be attacked equally from both sides, yielding a truly racemic product. This delicate interplay between ion pair stages and nucleophilic attack is absolutely crucial for understanding the diverse stereochemical outcomes we see in real-world SN1 reactions.
So that's the SN1 story, a two-step ionization influenced by stability, leaving groups, solvent, sterics, and these really critical ion pair nuances.
Couldn't have said it better myself.
Now let's pivot. Let's talk about the other limiting case.
Yeah.
The SN2 mechanism. Direct displacement. Completely different principle, right?
Completely different. The SN2 mechanism is a concerted process. That means bond breaking and bond forming happens simultaneously in one smooth step.
No intermediates. No valleys on the energy diagram.
Exactly. No stable intermediates, just a single higher energy transition state. The nucleophile approaches and attacks the carbon from the backside precisely 180 degrees opposite to where the leaving group is attached.
Backside attack. That's the signature move.
It is. As the new bond forms between the nucleophile and the carbon, the old bond to the leaving group breaks, all in one synchronized motion. The carbon atom momentarily passes through a trigonal bipyramidal geometry in this transition state.
And the kinetics are different too.
Markedly different. For SN2, the rate depends on both the reactant concentration and the nucleophile concentration. The rate law is rate equal tau KRXY.
Which is why it's called bimolecular, two molecules involved in that single rate-determining step.
Correct. This direct dependency on the nucleophile's concentration and identity is one of the clearest ways to distinguish it experimentally from SN1, where the nucleophile doesn't affect the rate of the slow step.
Okay, so the energy profile for SN2, simpler than SN1.
Much simpler. You just visualize a single energy barrier representing that one concerted transition state. No intermediate valleys to worry about.
And why the backside attack? Why is it so specific?
To really grasp that, we need to think about molecular orbitals. It's about optimal overlap. The nucleophile brings its highest occupied molecular orbital, or HOMO basically, its available electron pair.
Okay.
And that needs to interact effectively with the carbon-leaving group bond's lowest unoccupied molecular orbital, or LUMO specifically, the antibonding orbital. This antibonding orbital has a large lobe on the carbon atom pointing directly away from the leaving group.
So the backside approach lines up the nucleophile's electrons perfectly with that empty antibonding orbital lobe.
Exactly, like two puzzle pieces clicking perfectly into place. This orbital interaction initiates the bond formation and simultaneously weakens the bond to the leaving group.
And as this happens, the carbon's shape changes.
It momentarily flattens out and then inverts its configuration as it passes through that trigonal bipyramidal transition state. As the leaving group departs and the carbon settles back into its tetrahedral shape in the product, the overall configuration at that carbon center is precisely inverted.
Like an umbrella turning inside out in the wind.
That's the classic analogy, and it's perfect. This consistent, predictable inversion of configuration is a definitive hallmark of the SN2 mechanism.
Okay, so if the attack has to be from the backside, that must mean crowding is a big issue for SN2.
A massive issue, incredibly sensitive to steric bulk around the reacting carbon. Think about trying to thread a needle in a really crowded room. It's difficult.
So small, unhindered reactants are best.
By far. Methyl halides, CH3X, react fastest because the nucleophile has a clear path to the backside of the carbon. Replace just one hydrogen with an alkyl group, like going from methyl to ethyl, CH3CH2X, and the rate drops significantly. Go to isopropyl, CH3-2CHX, it drops even more.
And a tertiary carbon, like
Yeah.
CH3-3CX.
Forget about it. A tertiary carbon, completely surrounded by three bulky alkyl groups, effectively shuts down the SN2 mechanism entirely. There's just no room for the nucleophile to get in for that backside attack. Steric hindrance is fatal for SN2.
What about the leaving group in SN2? Still important.
Still important, yes. Just like in SN1, the leaving group still has to depart with an electron pair, so its stability matters.
Good.
Because the nucleophile is actively assisting its departure in SN2, it's pushing from the back as the leaving group pulls from the front. The reaction is generally less sensitive to the leaving group's intrinsic ability compared to SN1.
Ah, because in SN1, the leaving group has to do all the work itself in that first step.
Exactly. In SN1, the bond cleavage is unassisted. In SN2, the nucleophile lends a helping hand, so the leaving group's quality, while still a factor, doesn't impact the rate quite as dramatically.
Okay, that distinction makes sense. But you mentioned earlier that the lines between SN1 and SN2 can get blurry.
They definitely can. While the kinetic and stereochemical hallmarks we just discussed, unimolecular versus bimolecular kinetics, racemization versus inversion seem clear-cut on paper, in practice things aren't always so neat.
How so?
Well, one major practical challenge is something called pseudo-first-order kinetics.
Pseudo-first order. Sounds tricky.
It can be misleading. Imagine a reaction where the nucleophile is also the solvent, a solvolysis reaction. The solvent is present in such a huge excess compared to the reactant.
Its concentration basically doesn't change during the reaction.
Precisely. Even if the solvent molecule is participating in the rate-determining step, making it fundamentally bimolecular, SN2, the kinetics will look like their first order because the solvent concentration term is effectively constant.
So just looking at the rate law might fool you into thinking it's SN1 when it's actually behaving more like SN2 with solvent participation.
Exactly. Kinetics alone might not always tell the whole story.
And stereochemistry can be ambiguous too.
Yeah.
Not always perfect inversion or race comization.
Very often, yes. While complete racemization, ideal SN1, or complete inversion, ideal SN2, are the theoretical limits, many real-world substitution reactions show partial inversion or sometimes partial racemization mixed with inversion.
Why would that happen?
It points towards those more complex borderline mechanisms. Some reactions might show inversion, but have other characteristics suggesting an SN1-like pathway, maybe involving those ion pairs we talked about where attack happens before full dissociation. Secondary alkyl systems and also primary and secondary benzylic systems are often the culprits here. They sit right in that murky middle ground where a simple SN1 or SN2 label just doesn't capture the full picture.
And this is where the idea of a mechanistic continuum really comes into play, right? It's not just one or the other.
Precisely. It's a spectrum, not a switch.
Okay, building on that idea of borderline behavior and the blurry lines, we really need to think beyond just SN1 and SN2 as two separate boxes.
Absolutely. It's much more useful to see them as two ends of a broader mechanistic spectrum, a continuum.
So pure SN1 at one end.
Right, where there's zero covalent interaction between the reactant and the nucleophile during that initial bond cleavage step. The molecule ionizes all by itself.
And pure SN2 at the other end.
Where bond formation and bond breaking are perfectly synchronized, fully concerted.
And in between lies the mystery zone.
Exactly. That's the fascinating borderline region. Here, the nucleophile does have some degree of interaction, some participation in the bond-breaking step, but it's not a fully concerted single-step attack like classic SN2.
And this is where Saul Winstein's concept of ion pairs becomes absolutely essential.
Couldn't be more crucial. His insight was that ionization isn't an instant jump from reactant to free ions. He proposed that journey we discussed earlier.
Right, the stages. Contact ion pair, solvent-separated ion pair, then full dissociation.
Exactly. First, the contact or intimate ion pair, where the T cessation and its counter ion, the leaving group, are right next to each other.
Still very close.
Then solvent molecules wiggle their way in, creating the solvent-separated ion pair. They're still linked by electrostatics, but with that solvent cushion.
More distance.
And finally, full dissociation, where the ions are truly free agents, symmetrically solvated and independent.
And the power of this idea is how it explains the weird stereochemistry we sometimes see.
Perfectly. It elegantly explains the variable stereochemistry, why sometimes you get inversion, sometimes retention, sometimes racemization, or often mixtures. It depends entirely on which of these ion pair stages the nucleophile attacks.
Okay, remind me again. Attack on the contact pair.
Attack on the contact ion pair usually leads to inversion. Why? Because the leaving group anion is still physically blocking or electrostatically repelling the nucleophile from that face.
Makes sense. What about the solvent-separated pair?
Here, the nucleophile has more freedom to approach from either face. However, the leaving group, even though it's further away, or even the specific arrangement of solvent molecules might still subtly favor one approach over the other. This often leads to partial inversion, maybe mixed with some retention. It's fuzzier.
And the fully dissociated free carbocation.
That's your classic SN1 outcome. Symmetrical solvation means attack from either side is equally likely, leading to complete racemization. The precise stereochemical mixture you end up with tells you a story about the lifetime of these different ion pair species and when the nucleophile managed to jump in.
What's truly amazing is how chemists figured out how to actually see evidence for these fleeting ion pairs. It's not like you can isolate them easily.
No, they're incredibly short-lived, but yes, clever experimental designs provided compelling evidence. One really powerful technique uses isotopic labeling, often putting an oxygen-18 label into the leaving group, especially carboxylates or sulfonates.
Okay, so you label the leaving group, then what?
Then you compare two rates very carefully. First, the rate at which the starting material loses its optical activity, the rate of racemization, crack. Second, the rate at which that arrow label scrambles or exchanges within the unreacted starting material, kex.
Ah, so you're tracking if the leaving group comes off and goes back on without the molecule reacting further.
Exactly. If the rate of isotopic exchange is faster than the rate of racemization, crack, it tells you that an ion pair is forming, the leaving group is tumbling around or exchanging its oxygens, and then collapsing back to the starting material faster than the carbocation can fully racemize us. This internal return is direct evidence of ion pair formation and collapse.
Can you give an example?
A classic study involved p-chlorobenzhydryl p-nitrobenzoate with an O label in the carbonyl oxygen of the nitrobenzoate leaving group. They found kex was about 2.3 times faster than crack.
Meaning it returned internally more than twice as often as it racemized.
Precisely. And critically, this internal return happened with predominant retention of configuration. The contact ion pair was collapsing back faster than it could flip or become symmetric.
Wow. What happened when they added a better nucleophile, like ocoside?
That's where it got even more revealing. The rate of isotopic exchange, X, remained unchanged. The contact ion pair was still forming and returning just as fast, but now no racemization of the reactant was observed.
No racemization at all.
None. This meant that any ion pair that progressed beyond the contact stage, probably to the solvent-separated stage, was immediately snatched up by the azine ion before it had a chance to return and cause racemization. It beautifully demonstrated the distinct existence and reactivity of these different ion pair stages.
That's fascinating detective work. So it's not just a theory. There's real quantitative evidence.
Absolutely. We see similar behavior, this internal return phenomenon, quite often with secondary alkyl sulfonates, which frequently exhibit that borderline behavior. The extent of internal return can vary dramatically depending on the solvent, too.
How does solvent affect it?
In less nucleophilic solvents, the ion pairs might be more prone to dissociating further or reacting slowly with the solvent, so you see less internal return. But in more nucleophilic solvents, the solvent might stabilize the ion pair differently, or perhaps the return pathway is simply faster than solvent attack, leading to a much higher percentage of internal return. It really highlights the solvent's intimate role.
And they confirmed this exchange was happening within the ion pair.
Yes. Crucial control experiments often showed no exchange with external labeled anions added to the solution. This proved the scrambling or exchange was happening exclusively at one of the ion pair stages before full dissociation.
Are there other ways to detect ion pair return?
You can also compare the rate of loss of optical activity, polarimetry, with the rate of product formation, titration or spectroscopy. If your chiral starting material is racemizing faster than it's turning into product.
It means some intermediate is forming that can go back to racemic starting material.
Exactly. That intermediate is usually inferred to be the solvent-separated ion pair, which has lost the initial stereochemical information but hasn't yet reacted to form product.
And sometimes you get really weird results.
Yes, chemistry loves to keep us on our toes. There's a specific sulfonate example where isotopic scrambling was observed without any racethylamization in a particular solvent. The interpretation was maybe a contact ion pair where the sulfonate could rotate without migrating, or even a highly unusual front-side attack, though that's generally considered very unlikely. These edge cases continually refine our models.
Okay, so these ion pair stages are real, experimentally verifiable, and crucial for understanding that borderline behavior. How do they fit into the energy landscape?
The current thinking is that the energy barriers separating the covalent reactant, the contact ion pair, the solvent-separated ion pair, and the fully dissociated ions are often quite small. You can visualize them as relatively shallow dips and bumps on the energy profile.
Meaning they can interconvert rapidly.
Very rapidly. This makes their individual reactivity profiles, who attacks which stage and how fast, incredibly important in determining the final product distribution and stereochemistry.
So let's try to visualize that whole mechanistic continuum again. We have SN1 at one end, SN2 at the other.
Right. Think of it as a sliding scale of nucleophilic participation in the transition state. Pure SN1, zero participation. Pure SN2, maximum fully concerted participation.
And the borderline stuff fits in between.
Exactly. You can have mechanisms that look kinetically like SN1 but involve ion pairs. You can have mechanisms that involve some degree of nucleophilic assistance from the solvent or nucleophile in the transition state, even if that transition state still has significant carbocation character. It's not just black and white, it's shades of gray.
A chemist named Jenks had a useful way of thinking about this too, right? Relating it to carbocation lifetime.
Yes, William Jenks provided a very insightful framework connecting the stability and lifetime of the potential carbocation intermediate to this mechanistic continuum.
How did he break it down?
He described the ideal SN1 case, the limiting SN1, where the carbocation intermediate is relatively long-lived. It has time to equilibrate with the solvent, maybe rearrange before being captured. There's a definite energy minimum for that intermediate.
Okay, the classic picture. What happens as the carbocation gets less stable?
Its lifetime shortens dramatically. The energy barrier for it to be captured by a nucleophile gets smaller and can eventually disappear altogether. Jenks called this the uncoupled mechanism. Here, ionization still happens without nucleophilic participation, so you still see first-order kinetics like SN1, but the carbocation doesn't exist as a truly free, equilibrated intermediate. It gets captured almost immediately after forming.
So SN1 kinetics, but no real intermediate valley on the energy diagram.
Essentially, yes. Then, if the carbocation stability drops even further, the ion pair's lifetime becomes so vanishingly short that it must be captured by a nucleophile essentially as it forms, or even slightly before full bond breakage. This requires the nucleophile to be involved in the rate-determining step, leading to second-order kinetics. This is the coupled substitution process.
And if the potential carbocation is just way too unstable to form at all?
Then you're back to the other extreme, direct displacement, the pure SN2 limb mechanism. The nucleophile has to do all the work.
You mentioned an exploded SN2 transition state earlier. Where does that fit in?
That fits into the coupled region, often describing reactions that show second-order kinetics but still have significant carbocation character at the transition state. Think of reactions like atomizai attacking 1-phenylethyl chlorides.
What does exploded mean in this context?
It's a physical description suggesting that in the transition state, the bonds to both the incoming nucleophile and the outgoing leaving group are relatively long and weak. The central carbon atom carries a substantial amount of positive charge, much more than in a typical SN2 transition state. But crucially, bond rupture and bond formation are still concurrent. It's a stretched out, precarious, high-energy state, sort of halfway between SN1 and SN2 character, but kinetically behaving like SN2.
So this model helps explain how some reactions can look like SN2 kinetically, but feel like SN1 electronically.
Exactly. It helps rationalize systems like certain secondary sulfonates that show second-order kinetics but are also very sensitive to factors that stabilize positive charge. It really bridges that gap in the continuum.
This whole picture, concerted SN2, ion pairs, stepwise SN1, coupled versus uncoupled, exploded transition states, it all fits together into one unifying energy landscape. It feels much more complete than just SN1 versus SN2.
It is. It provides a much more nuanced and accurate framework for understanding the huge diversity of substitution reactions we observe.
And again, the solvent must play a huge role in navigating this continuum.
Oh, absolutely critical. Solvent choice is one of the tools chemists have to push reactions towards one end of the spectrum or the other.
How did that work?
Solvents with very low nucleophilicity, think trifluoroacetic acid, TFA, or highly fluorinated alcohols, are great for studying pure ionization behavior. They minimize any solvent participation in the bond-breaking step, essentially forcing the molecule to ionize on its own if it's going to. They help define the SN1 end of the spectrum.
And more nucleophilic solvents.
Solvents like ethanol, water, or acetic acid are much more likely to participate nucleophilically. They can jump in to assist bond breaking or rapidly trap intermediates, pushing reactions towards the SN2 or borderline regions.
Is there a benchmark system chemists use to gauge solvent participation?
Yes. The two-atom mantle system is a classic. Its rigid, cage-like structure makes backside attack by the solvent physically impossible.
So any substitution must proceed via ionization without solvent help.
Exactly. It's the perfect model for studying pure SN1 ionization characteristics. By comparing the rates and behavior of other substrates to the two-atom mantle system in various solvents, chemists can get a really good estimate of how much the solvent is participating nucleophilically in those other reactions. It's a clever way to dissect the mechanism.
All right, so we've really dug into the mechanisms, the continuum, the ion pairs. It's fascinating stuff. Now let's talk about some of the other key players that influence these reactions. The supporting cast, if you will.
Good analogy. Things like the leaving group, steric effects, and conjugation can have a huge impact.
Let's start with leaving group ability. We touched on it, but what really makes a good leaving group?
Fundamentally, a good leaving group needs to be stable on its own after it takes that pair of electrons and departs from the carbon.
Stable how?
Well, its stability correlates with a couple of things. One is the strength of the bond it originally formed with carbon. Weaker bonds are easier to break. But perhaps more importantly, it relates to the stability of the resulting anion or neutral molecule. And that stability is directly related to the acidity of its conjugate acid.
Oh, okay. So strong acids have stable conjugate bases.
And those stable conjugate bases make excellent leaving groups. Think about hydriodic acid, HI. It's a very strong acid, so iodide, I up, is a very stable anion and thus a fantastic leaving group. Conversely, hydrofluoric acid, HF, is a weaker acid, so fluoride is a less stable anion and a poor leaving group. The carbon-fluorine bond is also very strong, adding to its reluctance to leave.
And we can see really big differences in reactivity based on the leaving group.
Dramatic differences, orders of magnitude. If you look at solvolysis rates, replacing a mediocre leaving group like acetate with an excellent one like trifluoromethane sulfonate, commonly called triflate.
Triflate. Yeah, I hear that one a lot.
You can see rate increases of 10 or 10 out, maybe even more. It's incredibly reactive. Sulfonate esters in general, like tosylates, OTs, and mesylates, OMs, are workhorses in organic synthesis for this reason.
Why are they so useful in synthesis?
Because you can easily make them from alcohols using the corresponding sulfonyl chloride, and crucially, this preparation step doesn't usually affect the stereochemistry at the carbon atom where the substitution will later occur. You activate the alcohol for substitution without scrambling its configuration.
That's clever. And the halide trend we mentioned, IBRCLF.
That holds very consistently. It's primarily driven by the CX bond strength, weakest for CI, strongest for CF, and the stability of the halide anion, IO being the largest and most stable.
Now, does the mechanism SN1 versus SN2 affect how important the leaving group is?
Yes, significantly. SN1 reactions are much more sensitive to leaving group ability than SN2 reactions.
Why is that?
Remember, in the rate-determining step of SN1, the leaving group has to depart all by itself, completely unassisted by the nucleophile. Its inherent ability to leave is therefore paramount.
Whereas in SN2, the nucleophile is helping push it out.
Exactly. That nucleophilic assistance in SN2 means the reaction is less reliant on the leaving group's intrinsic desire to leave. We see this experimentally. Compare the rate ratio for a good leaving group versus a moderate one, say tosyl bromide. For a primary system reacting via SN2, the ratio might be around 10 or 20. But for a tertiary system reacting via SN1, that same ratio can jump to several thousand.
Wow, that's a huge difference. Clear evidence for the different dependencies.
Absolutely. It's a great diagnostic tool. SN2 reactions show diminished leaving group effects compared to SN1.
Okay, so what if you're stuck with a really bad leaving group, like the hydroxide group in an alcohol? You said it doesn't leave easily.
It's terrible on its own. The energy required for it to just pop off as hydroxide ion is estimated around 16 kilopalmol endothermic. That's a big barrier. Direct substitution on neutral alcohols rarely happens.
So you have to activate it somehow.
Precisely. The classic trick is to protonate it using a strong acid. Adding a proton to the oxygen turns OH into O-suburose.
Ah, and now the leaving group is?
A neutral water molecule. HERO is an excellent leaving group, very stable on its own, comparable to bromide. This is exactly why you can convert alcohols to alkyl bromides just by heating them with concentrated hydrobromic acid, HBr. The acid protonates the alcohol, making water the leaving group, which then gets displaced by bromide ion.
Clever. Are there other ways to activate poor leaving groups?
Yes, Lewis acids can also do the trick. For example, silver ions, agar, can coordinate to alkyl halides, especially iodides and bromides, helping to pull off the halide anion and facilitating carbocation formation. Antimony pentafluoride, SBFOs, is extremely effective at abstracting halide ions too, especially in those superacid studies. It's all about making that leaving group more willing to depart.
Okay, let's shift gears to steric effects molecular crowding. We already established that for SN2, hindrance is basically fatal.
Absolutely lethal. Increased steric bulk around the reacting carbon dramatically slows down SN2. That required backside attack path gets blocked.
Can we see this in data?
Clearly. Look at the rates of SN2 reaction for simple alkyl bromides with a given nucleophile. Methyl bromide is the fastest. Ethyl bromide is significantly slower. Isopropyl bromide, CHBr, is slower still. And tertiary butyl bromide. The rate is essentially 0 under typical SN2 conditions. The trend is stark. Me 1 degrees, 2 degrees, 3 degrees for SN2 reactivity.
And systems like neopentyl bromide, where the branching is 1 carbon away.
Neopentyl systems, CH-CHER, are also notoriously resistant to SN2, even though the reaction center is primary. Those bulky T-butyl groups nearby effectively shield the backside from attack. Sterics are paramount for SN2.
But then for SN1, you said hindrance can actually be a friend. This still feels weird.
It does seem counterintuitive, but it's true in many cases. Remember, SN1 rates generally increase with substitution. 3 degrees, 2 degrees, 1 degree more.
Right, because of carbocation stability. Tertiary carbocations are the most stable.
That's the primary reason, yes. More substituted carbocations are better stabilized by hyperconjugation from the alkyl groups. But there's also that secondary factor we mentioned, B strain or backstrain.
The relief of crowding when going from tetrahedral to planar.
Exactly. If the initial tetrahedral reactant is sterically congested, maybe with several bulky groups squeezed together, it's under strain. Ionizing to a planar, hybridized carbocation allows those groups to spread out, relieving that strain.
So the strain in the starting material actually pushes the reaction towards ionization.
It can significantly lower the activation energy for ionization. We see examples where adding more bulky groups near the reaction center, which would kill an SN2 reaction, actually accelerates an SN1 reaction, sometimes by factors of thousands, purely due to the relief of this B strain upon forming the less crowded carbocation.
Mind blown. Okay, so sterics, bad for SN2, potentially good for SN1 if it relieves strain. What about conjugation? How do pi systems affect these reactions?
Conjugation provides a nice boost, often to both SN1 and SN2, especially in allylic next to CC, and benzylic next to a benzene ring systems. These are usually unusually reactive.
Why are they good for both?
For SN1, it's again about carbocation stability. An allylic or benzylic carbocation is highly stabilized because the positive charge can be delocalized into the adjacent pi system, the double bond or the aromatic ring, through resonance. This makes the carbocation much easier to form.
Okay, that makes sense for SN1. How does it help SN2?
For SN2, the pi system can help stabilize the transition state. Remember that trigonal bipyramidal transition state? The developing orbital on the central carbon as it rehybridizes can overlap with the adjacent pi system. This extended conjugation lowers the energy of the transition state, reducing the activation barrier and speeding up the reaction. It's an orbital interaction effect.
So allylic and benzylic systems get a win-win from conjugation.
Nice. What about carbonyl groups? You mentioned they have an unexpected effect.
Right. Alpha carbonyl compounds, where you have a CO group right next to the reacting carbon, like in alpha haloketones, they generally destabilize carbocations because the carbonyl is electron withdrawing, so they slow down SN1 reactions.
Okay, that fits. But they accelerate SN2. Yes, often quite significantly. An alpha chloroketone, for example, can undergo SN2 much faster than a simple alkyl chloride.
How does that work if the carbonyl is electron withdrawing?
2 factors. Minor one. The Spock carbon of the carbonyl is less sterically bulky than a Spock alkyl group. Major one. Electronic stabilization of the transition state.
How?
The adjacent carbonyl group has a low-lying empty pi antibonding orbital, the LUMO. In the SN2 transition state, electron density builds up on the central carbon as the nucleophile attacks. This electron density can effectively delocalize into that adjacent carbonyl orbital.
Like the carbonyl is acting as an electron sink.
Precisely. It stabilizes the electron-rich transition state through a kind of resonance interaction, forming an enolate-like structure. This significantly lowers the activation energy for the SN2 process.
Very cool. But you said not all electron withdrawing groups do this.
Correct. It highlights the specific type of electronic interaction required. Groups like sulfonyl, SO uros, or trifluoromethyl, CF uros, which are strongly electron withdrawing by induction, but cannot participate in this kind of pi electron acceptance via resonance.
They don't have that low-lying pi orbital in the right place.
Exactly. They actually retard SN2 reactions at an adjacent carbon due to their inductive electron withdrawal, destabilizing the transition state. It really emphasizes the need for that specific acceptor interaction for acceleration, not just general electron withdrawal. It's all in the details of the orbitals.
Okay, we've covered the core mechanisms, the continuum, and the key external factors like leaving groups and sterics. Now, let's dive into something really neat. When the molecule itself gets involved in the reaction, neighboring group participation.
Ah, yes, NGP. This is when a functional group within the reacting molecule acts as an internal nucleophile. And when this happens, it can have truly dramatic effects on both the reaction rate and the stereochemistry. Often leads to unexpected outcomes if you're only thinking about simple SN1 or SN2.
Give us a classic example.
The textbook case is often acetoxy group participation. Consider 2-acetoxycyclohexyl tosylate. You can have two distereomers. Cis, where the acetoxy and tosylate are on the same face of the ring, and trans, where they're on opposite faces.
Okay, cis and trans. What happens when they react, say, in acetic acid?
The difference is stunning. The trans isomer reacts about 670 times faster than the cis isomer.
Whoa, 670 times faster. Why?
And the stereochemistry is even more revealing. The cis isomer reacts as you might expect for a secondary system, mostly with inversion of configuration. But the trans isomer, it reacts with overall retention of configuration, and the product formed is completely racemic, even if you start with optically pure trans isomer.
Retention and racinization. That breaks all the simple rules. How does the neighboring acetoxy group cause that?
It's beautiful mechanism. In the trans isomer, the acetoxy group is perfectly positioned on the opposite face from the leaving group, the tosylate. As the tosylate starts to leave, the carbonyl oxygen of the nearby acetoxy group swings around and provides backside assistance. It attacks the reacting carbon from within the molecule.
An intramolecular SN2 attack.
Essentially, yes. This forms a cyclic bridged intermediate called an acetoxonium ion. It's a 5-membered ring containing the oxygen. Crucially, this acetoxonium ion intermediate is axial. It usually has a plane of symmetry.
Axial intermediate. Okay, I see where this is going.
Because the intermediate is axial, when the external nucleophile, the acetic acid solvent in this case, comes in to attack and open up this bridged ion, it can attack either of the two equivalent carbons from the opposite face. This leads to a 50.50 mixture of enantiomers, a racemic product.
And because the initial attack was backside, intramolecular, and the second attack was also backside, intermolecular, opening the ring, the overall stereochemistry relative to the original leaving group is retention.
You nailed it. Intramolecular backside attack followed by intermolecular backside attack results in net retention. The rate acceleration comes from the fact that this intramolecular attack is highly efficient. The nucleophile is tethered right there, ready to go. The cis isomer can't do this, so it reacts much more slowly via other pathways.
Have these acetoxonium ions ever been, trapped or observed?
Yes, absolutely. If you run the reaction in a different nucleophilic solvent like ethanol, you can sometimes isolate stable cyclic orthoester products, which are effectively the result of the alcohol trapping that acetoxonium ion intermediate. Powerful evidence.
So it's not just acetoxy groups. Other groups can do this too, like hydroxyl or alkoxy or OCAR groups.
Instantly. Hydroxy and alkoxy groups can participate similarly, forming cyclic ether intermediates, oxonium ions. For example, 4-chlorobutanol solvolizes much, much faster than, say, 3-chloropropanol or 5-chloropentanol.
Why the 4-chloro specifically?
Because the hydroxyl group in 4-chlorobutanol is perfectly positioned to attack the carbon bearing the chlorine via an intramolecular backside displacement, forming a highly stable 5-membered ring tetrahydrofuran THF after proton loss.
Ring size matters. 5-membered rings are generally easy to form.
Very much so. 3- and 4-membered rings have significant ring strain, and larger rings suffer from unfavorable entropy. It's harder for the ends of a long chain to find each other. 5- and 6-membered ring formation through NGP is often kinetically preferred. We see this consistently in rate data for cyclizations.
And if you make the internal nucleophile even better, like deprotonating a hydroxyl to an alkoxide,
then the participation becomes even more dramatic. Take 2-chloroethanol. In neutral water, it reacts slowly. But in basic solution, where it gets deprotonated to the alkoxide anion, it reacts thousands of times faster than ethyl chloride, rapidly forming ethylene oxide, a 3-membered epoxide ring. That internal alkoxide is a potent nucleophile.
Okay, so oxygen atoms are good neighbors. What about pi electrons? Can double bonds or aromatic rings act as neighboring groups?
Yes, and this leads to some truly spectacular rate accelerations and interesting rearrangements. Pi electron participation is a major phenomenon.
Give us an example.
The classic is the solvolysis of norbornyl tosylates. Compare anti-7 norbornyl tosylate, where the tosylate is on the opposite side of the molecule from the double bond, with its saturated analog, norbornyl tosylate.
Okay, double bond versus no double bond. How different are the rates?
In acetic acid, the anti-norbornyl tosylate reacts an astonishing 10 unique times faster than the saturated compound.
10 to the 11th. That's astronomical. 100 billion times faster.
Astronomical is right.
Right.
And the product is formed with retention of configuration.
How on earth does the double bond cause that level of acceleration?
As the tosylate leaving group departs, the pi electrons of the double bond, perfectly positioned underneath, reach up and participate directly in the ionization. They attack the developing positive charge, forming a highly stabilized, delocalized, non-classical carbocation intermediate.
A non-classical ion. We'll get more into those later, I bet.
We definitely will. But essentially, the charge is shared between the original carbon C7 and the two carbons of the double bond, C2 and C3, forming a bridged structure. This provides immense stabilization, hence the incredible rate enhancement. The syn isomer, where the tosylate is on the same side as the double bond, can't participate like this and reacts much, much slower, often giving rearranged products. Geometry is everything here.
So the pi clad is literally acting as the internal nucleophile, assisting the departure. Can it form new bonds too?
Yes, sometimes the participation results in cyclization. For example, 2-cyclopent-3-N-lithyl tosylate undergoes solvolysis to form bicyclic products, clearly showing a new carbon-carbon bond formed by the double bond attacking the reaction center.
Amazing. Okay, what about aromatic rings? Can a benzene ring participate?
Yes, this is known as aryl participation, and it also involves the formation of a bridged intermediate called a phenonium ion.
Phenonium ion. Sounds fancy.
It is. It's where a phenyl group on a carbon-adjacent, beta, to the leaving group bends over and uses its pi electrons to attack the reaction center as the leaving group departs. This forms a three-membered ring fused to the benzene ring, with the positive charge delocalized into the aromatic system.
How do we know these form?
Again, stereochemistry provides compelling evidence. Donald Cram did pioneering work on the 3-phenyl-2-butyl tosylate system. He showed that the erythrodiastereomer solvolized primarily with retention of configuration, consistent with forming a chiral-bridged phenonium ion. But the 3-O-diastereomer gave a racemic product, consistent with forming an equiral symmetrical phenonium ion intermediate.
Just like the acetoxonium ion case, but with a benzene ring doing the bridging.
Exactly the same logic. And again, we can quantify this participation. Chemists often dissect the overall rate into two components. K's, the rate constant for direct solvent displacement, and K, the rate constant for the aryl-assisted pathway. By studying substituent effects on the phenyl ring using Hammett plots, you can separate these contributions.
And solvent matters here too.
Hugely. In highly nucleophilic solvents, direct solvent attack can compete effectively, reducing the amount of product formed via the phenonium ion. But in poorly nucleophilic solvents like formic acid or TFA, where the solvent is less likely to intervene, the aryl-assisted pathway becomes much more dominant, leading to more rearrangement and retention racemization via the phenonium ion.
And have these phenonium ions been directly observed?
Yes. Similar to other stable carbocations, phenonium ions have been generated and characterized by MR spectroscopy in superacid media, confirming their bridged structure. It's another beautiful example of internal participation dramatically altering the course of a reaction.
We've seen how neighboring groups can steal the show, forming these fascinating bridged ions. But now let's really focus on the carbocations themselves, the primary intermediates in SN1 and many other reactions. Understanding their structure, stability, and reactivity is absolutely central.
Couldn't agree more. Carbocations are the heart of the matter in so many mechanistic discussions. First thing to remember, intrinsically they are very high-energy species.
High energy, like unstable.
Extremely unstable in isolation. Filming a simple tertiary butylcation, T-butyl plus, from isobutane in the gas phase, requires something like 153 kilocoulomb. That's a huge amount of energy. A reaction needing that much activation energy would simply never happen under normal conditions.
But they clearly do form in solution, so what makes them accessible?
Solvation. The interaction of the carbocation with surrounding solvent molecules dramatically stabilizes it, lowering its energy significantly. Polar solvents are particularly good at this, clustering around the positive charge and spreading it out electrostatically. Solvation makes carbocation formation energetically feasible in solution.
So how do we actually measure or compare their stability in solution? It's not like you can just put them in a bottle and weigh them.
Right. For relatively stable carbocations, especially those stabilized by resonance like triaryl methylations, chemists developed the pKr plus scale.
pKr plus HARO.
It's analogous to pKr for acids. It's essentially the pH at which the carbocation, R, and corresponding alcohol, ROH, are present in equal concentrations in an equilibrium in acidic solution. Rho plus H0, ROH plus H.
So a less negative pKr plus means the carbocation is more stable.
It can exist in less acidic conditions.
Exactly. More stable carbocations have less negative or even positive pKr plus values. You can clearly see the effect of substituents. Electron-releasing groups like methoxy or amino on the phenyl rings make the pKr plus much less negative, more stable cation, while electron-withdrawing groups make it more negative, less stable cation.
And you mentioned cyclopropyl groups are amazing stabilizers.
Exceptionally good. Tricyclopropylmethylpation is significantly more stable than even the triphenyl methyl elementylcation, according to pKr plus data. The bent bonds of the cyclopropane ring are very effective at donating electron density to the positive charge.
Okay, pKr plus is one way. Are there others?
Another useful measure, applicable to a wider range of carbocations, including simple alkyl ones, is hydride affinity.
Hydride affinity.
It's the negative of the enthalpy or free energy change for the reaction, ρ plus HRH. Basically, how strongly does the carbocation want to grab a hydride ion to become a neutral alkane?
So a higher hydride affinity means the carbocation is less stable. It wants the hydride more.
Precisely. Less stable carbocations have higher hydride affinities. We have values for both the gas phase and solution. While the absolute numbers are much smaller in solution due to solvation effects, the relative stability trends, for example, tertiary, secondary, primary, are generally preserved.
Can we study them without solvent getting in the way too much?
Yes, using those superacid media, we talked about strong Lewis acids like SBFU and non-nucleophilic solvents like ester, ERO, ER. This allows us to generate carbocations from precursors like alkyl halides and measure their relative stabilities, often by looking at equilibria between different cations, with minimal interference from the solvent acting as a nucleophile.
And do these superacid studies match the gas phase trends?
They correlate quite well, confirming the intrinsic stability order. Interestingly, though, the energy gap between, say, tertiary and secondary carbocations is significantly smaller in solution, 9.5 kilocarbical, compared to the gas phase, 17 kilopol.
Why the smaller gap in solution?
It highlights how effectively solvation stabilizes less substituted carbocations. While tertiary is still more stable, the solvent helps bridge the gap by providing more stabilization to the secondary ion than it might receive intrinsically. Solvation levels the playing field somewhat.
Okay, so we know tertiary, secondary, primary stability. But why? What's the fundamental reason alkyl groups stabilize carbocations?
The primary mechanism is hyperconjugation.
Hyperconjugation. Sounds important. What is it?
It's a stabilizing interaction that involves the delocalization of electron density from adjacent sigma bonds, usually CH bonds, but also CC bonds, into the empty p orbital of the carbocation center.
So electrons from a nearby single bond are sort of leaking over into the empty orbital on the positive carbon.
That's a great way to picture it. It's like the sigma bond electrons are partially shared with the electron-deficient center, helping to spread out that positive charge. The more adjacent CH or CC bonds there are, the more hyperconjugation is possible, hence the stability order. Tertiary, most alkyl groups. Secondary, primary, methyl. No alkyl groups.
Is there direct evidence for hyperconjugation?
Oh yes, plenty.
Such as?
NMR spectroscopy shows subtle changes in chemical shifts consistent with charge delocalization. X-ray crystallography of stable carbocations, like the T-butyl stamication, confirms the expected planar geometry at the positive carbon and often shows slightly shortened CC bonds adjacent to it, indicating some partial double bond character from hyperconjugation.
And calculations.
Sophisticated computational studies beautifully visualize this. They show, for instance, a slight elongation of the specific CH bonds that are properly aligned to donate into the empty p orbital. Charge analysis calculations confirm that electron density is indeed transferred from the adjacent hydrogens and carbons towards the cation medium center.
Can CC bonds participate as effectively as CH bonds?
Yes. Calculations on ions like the 2-methyl-2-butyl conjugation show that CC hyperconjugation can be just as important, sometimes even more so, than CH hyperconjugation, depending on the geometry and alignment.
And this electron sharing, what are the consequences beyond just stabilization?
Hyperconjugation has profound implications for reactivity.
Like what?
Well, if the electron sharing becomes very significant, it can lead to those bridge structures we discussed earlier, where a hydrogen or alkyl group is essentially shared between two carbons via a three-center bond. It's also the driving force behind 1-word-2 rearrangements, hydride shifts, and alkyl shifts, where a group moves over to form a more stable carbocation. That migration happens because the adjacent sigma bond electrons are already interacting with the empty p orbital.
So hyperconjugation sets the stage for rearrangement.
Absolutely. And it also sets the stage for elimination reactions, E1 mechanism. By donating electron density away from adjacent CH bonds, hyperconjugation weakens those bonds slightly, making the protons more acidic and susceptible to being removed by a base or even the solvent, leading to alkene formation. It's a direct competitor to substitution.
Fascinating link between stability and reactivity pathways. What about other substituents directly attached to the cationic carbon we know alkyl groups stabilize? What about groups with lone pairs, like oxygen or nitrogen?
Atoms with lone pairs directly attached to the carbocation center are incredibly stabilizing. Oxygen, like in an alkoxy group, OR, nitrogen, like in an amino group, NOR, and even halogens, F, Cl, Br, can donate a lone pair directly into the empty p orbital.
How does that stabilize?
It forms a pi bond, essentially creating a double bond between the heteroatom and the carbon. This is hugely favorable because it satisfies the octet rule on the carbon atom, giving it a full valence shell, even though it places a formal positive charge on the more electronegative heteroatom like O or N.
So completing the octet outweighs putting positive charge on oxygen.
Often, yes. This resonance stabilization is typically much more powerful than inductive effects or even hyperconjugation. It's why cations like the methoxymethyl cation are surprisingly stable. There's actually a significant barrier to rotation around the CO bond in such cations, proving that double bond character.
Okay, lone pair donors are great stabilizers. What about strong electron withdrawing groups directly attached, like trifluoromethyl, CO-Air, or cyano-CN?
They are strongly destabilizing, as you'd expect from their powerful inductive electron withdrawal, the polar effect. A CF Euro group attached to a carbocation makes it much, much harder to form.
Are they all equally bad?
Interestingly, no. Groups like cyano-CN and formal-CHO, while definitely destabilizing overall, are less destabilizing than you might predict based solely on their inductive effects.
Why the discrepancy?
Because these groups, although electron withdrawing through the sigma system, can act as weak donors through resonance. They have pi electrons in the CN or CO bond that can be partially donated back towards the carbocation center.
Wait, the electron withdrawing group acts as a donor.
Through resonance, yes. It involves drawing resonance structures where there's a positive charge on the nitrogen or oxygen, which isn't ideal, but it still provides a small degree of resonance stabilization that partially counteracts or attenuates the powerful destabilizing inductive effect. It's another subtle interplay of effects.
Chemistry is full of these push-pull effects. Okay, we also touched on geometry being critical. If the carbocation can't become planar,
if geometric constraints prevent the carbon atom from achieving that ideal trigonal planar Spes-Rod geometry, carbocation formation becomes extremely difficult or even impossible.
what's the classic example of this?
One, chloroapocampane. It's a tertiary chloride, so you might expect it to undergo SN1 readily, but it's completely inert to substitution under conditions that readily ionize other tertiary chlorides.
Why is it inert?
Because it's part of a rigid bicyclic cage structure. The bridgehead carbon, where the chlorine is attached, simply cannot flatten out to become planar spied. The strain energy required to force it into that geometry is prohibitively high. Backside SN2 attack is also impossible at a bridgehead. It's trapped.
So planarity is absolutely essential for typical carbocation formation.
For low energy formation, yes. We see this trend clearly in the solvolysis rates of other bridgehead halides. Systems like 1-bromodomantane, which is relatively less strain at the bridgehead, react much faster than more strained systems like 1-bromobicyclo-2.2.1 The rates correlate directly with the calculated strain energy involved in forming a non-planar carbocation at the bridgehead.
What about other non-ideal geometries, like vinyl cations?
Alkanol, or vinyl, cations where the positive charge is on a cis-hybridized carbon of a double bond are also quite unstable, roughly 15 kilocalmol higher in energy than a comparable secondary alkyl carbocation. This is partly due to the higher electronegativity of spur orbitals compared to sposoma. They are very reactive intermediates, but they can be formed, especially using highly reactive leaving groups like triflates, and often lead to products like alkenes or alkanes.
And the phenyl cation. Positive charge on a benzene ring carbon.
Extremely unstable, even worse than vinyl cations. The empty orbital on the spur carbon is in the plane of the ring, perpendicular to the pi system, so it gets absolutely no stabilization from the aromatic pi electrons. Phenyl cations are usually generated from precursors like aryl diazonium ions, but are highly reactive intermediates.
Okay, so we have all this understanding of stability and structure. How did chemists actually confirm these ideas by directly observing these often fleeting species?
That was a major breakthrough, largely thanks to George Olah and the development of superacid chemistry in the 1960s, which earned him a Nobel Prize.
Superacids. What makes an acid super?
A superacid is defined as an acid system stronger than 100% pure sulfuric acid. A famous example is magic acid, a mixture of fluorosulfuric acid, FSOH, and antimony pentafluoride, SBFO, often used in a non-nucleophilic solvent like sulfur dioxide, SO-Euros, or sulfuryl chloride fluoride, SOClF, at very low temperatures.
Why are they so important for studying carbocations?
Two reasons. They are incredibly strong protonating agents, capable of forcing even weak bases like alkanes or alcohols to form carbocations, and D, they are extremely non-nucleophilic. This means once the carbocation is formed, it doesn't immediately get quenched by reacting with the acid or solvent. It can persist long enough to be studied.
Studied how?
Primarily using NMR spectroscopy, especially LOH and AC NMR. At low temperatures in superacid media, even relatively unstable carbocations like secondary or tertiary alkylations can have lifetimes long enough to give well-resolved NMR spectra.
What did these NMR studies reveal?
They provided direct structural confirmation. For example, the NSC NMR spectrum of the T-butylhexane shows a single signal far downfield, around 330 ppm, indicative of a highly electron-deficient carbon, and confirms the equivalence of the three methyl groups, consistent with a planar or rapidly averaging structure. They also dramatically revealed the propensity of carbocations to rearrange.
Rearrange how?
If you generate, say, a secondary carbocation in superacid, it will often rapidly rearrange via hydride shifts or alkyl shifts to form the most stable possible isomeric carbocation. For example, almost any C4 precursor, like any isomer of butanol or butyl chloride thrown into superacid, ends up giving the NMR spectrum of the T-butylcation.
Yeah.
Any C5 or C6 precursor often rearranges to the 1-methylcyclopentyl annotation.
So in superacid, they rearrange until they reach the absolute thermodynamic minimum energy structure.
Exactly. Because there's no nucleophile around to trap them in an earlier, less stable form, they have ample time to undergo whatever rearrangements are necessary to reach the most stable isomer. This provides invaluable information about the relative stabilities and rearrangement pathways.
And calculations help confirm these structures.
Immensely. Modern computational methods, particularly those that calculate NMR chemical shifts like GIAO methods, can accurately predict the spectra for proposed carbocation structures. When the calculated spectrum matches the experimentally observed one in superacid, it provides very strong evidence for that structure.
Has anyone ever crystallized a simple carbocation? Gotten an X-ray structure?
Amazingly, yes. While challenging due to their reactivity, crystallographers have successfully obtained X-ray structures of some relatively stable cations, like triphenylmethyl and various cyclopropyl cations. Even more remarkably, the structure of the less stable T-butyl cation was determined by X-ray diffraction of its complex with a weakly coordinating anion, definitively confirming its trigonal planar geometry and showing the expected CC bond shortening due to hyperconjugation. Seeing is believing.
Incredible. Okay, one last point in this section. Once a carbocation forms, say in a more typical reaction solvent, it doesn't just rearrange or get trapped by a nucleophile substitution. There's another major competing pathway, right?
Yes, the ever-present competition. Substitution versus elimination.
The E1 pathway.
Exactly. The carbocation intermediate, once formed, is at a crossroads. It can react with a nucleophile, like the solvent, to give the substitution product, SN1 pathway, or it can lose a proton from a carbon atom adjacent to the positive center, forming a double bond, the elimination product, E1 pathway.
How does the energy profile look for this choice?
You can picture the carbocation sitting in that intermediate energy well. From there are two paths leading downhill. One path goes over a relatively small barrier to the substitution product. The other path goes over a different, also relatively small barrier where a base, often the solvent, removes an adjacent proton, leading to the elimination product, alkene.
Which pathway is usually preferred, substitution or elimination?
For typical solvolysis reactions of secondary and tertiary carbocations, substitution is often highly favored. For example, we mentioned the 1-butyl ethylcation gives an SE ratio of about 1400 in TFE water. Even the T-butylcation in water or aqueous ethanol typically gives SE ratios between 30 and 60.
Why does substitution usually win?
Good question. Thermodynamically, forming the CO bond in substitution is often stronger and more favorable than forming the CUC pi bond in elimination. Kinetically, it seems that the transition state for solvent capture substitution often has a lower intrinsic barrier than the transition state for proton removal elimination, especially when the solvent is acting as both nucleophile and base. The exact reasons are complex, relating to the degree of bond formation breaking in the respective transition states, but the empirical observation is that SN1 often dominates over E1 under solvolysis conditions. However, changing conditions, like using a strong non-nucleophilic base, can heavily favor elimination instead.
Okay, we've established carbocations are stable enough to observe, but also prone to competition between substitution and elimination. But you also emphasize how incredibly dynamic they are, especially regarding rearrangements. Let's explore that fluidity more.
Yes, rearrangements are truly a hallmark of carbocation chemistry. If you see unexpected products where the carbon skeleton seems to have changed, a carbocation intermediate is often the prime suspect.
And these rearrangements typically involve those 142 shifts.
Primarily, yes. A group, usually a hydrogen atom, hydride shift, or an alkyl group, alkyl shift, but sometimes alkenyl or aryl groups too, migrates from a carbon atom directly adjacent to the positively charged carbon, moving over to the positive carbon.
Taking its bonding electrons with it.
Exactly. The migrating group moves with its electron pair, leaving behind a positive charge on the carbon it just left. The net effect is that the positive charge moves to a different location in the molecule.
And the driving force is always to form a more stable carbocation.
Almost always. A primary carbocation will rapidly rearrange to a secondary or tertiary if possible. A secondary will rearrange to a tertiary. The activation energies for these 142 shifts are often remarkably small, sometimes less than 5 kilocoulomb.
That low, meaning they happen incredibly fast.
Extremely fast, even at very low temperatures in superacid. This explains why we often only observe the most stable isomer under those conditions. Any less stable ones rearrange almost instantaneously.
Now, you mentioned these shifts might involve bridged intermediates or transition states, not just a simple hop.
That's right. Especially for hydride shifts, the transition state is often thought to resemble a protonated cyclopropane. The migrating hydrogen is partially bonded to both the origin carbon and the destination carbon simultaneously, forming a 3-center 2-electron bond.
A hydrogen bridge.
Effectively, yes. Depending on the system, this bridge structure might be just the transition state, or in some cases, it could even be a fleeting intermediate. Calculations on the energy surface for propalcations, for instance, show the 2-propyl isopropalcation is the most stable, and the hydride migration converting 1-propyl to 2-propyl likely proceeds through a corner protonated cyclopropane-like transition state. For alkyl shifts, you can have similar alkyl bridge structures.
How do chemists actually map out these complex rearrangement pathways? It sounds like a maze.
It requires a combination of careful experiments, often using isotopic labeling, and high-level computational studies.
Let's take the two-butylcation again. What have studies shown there?
Under stable ion conditions in superacid, NMR shows incredibly rapid scrambling of hydrogens between C2 and C3 via a 12-2 hydride shift. The barrier is less than 2.5 kilomole, so fast it makes the ion look symmetrical on the NMR timescale. There's also slower scrambling between C3 and C4, likely involving an edge-protonated cyclopropane intermediate with a barrier around 7 to 8 kilomole, and then the even slower rearrangement to the most stable p-butyl ion has a barrier around 18 kilocoulomb.
Wow, multiple pathways with different speeds. And calculations support this.
Yes, molecular orbital calculations on the Ciereo-Bru potential energy surface show that hydrogen bridge and methyl bridge structures are indeed very close in energy to the open classical ions, potentially acting as intermediates or low-energy transition states for these scrambling processes.
How does this relate back to reactions in normal solvents like solvolysis?
It shows the potential for rearrangement is always there. When 2-butyl tosylate is solvolized, the extent of rearrangement depends on how fast the nucleophile solvent can trap the initially formed carbocation versus how fast the rearrangement occurs. In a good nucleophilic solvent like acetic acid, trapping is fast, and you see only about 9% hydride shift product.
But in a poor nucleophile like TFA,
trapping is slower, giving the rearrangement more time to happen. The extent of hydride migration approaches 50%, indicating the intrinsic rate of the Wal2 hydride shift is very fast, competitive with solvent capture even by a weakly nucleophilic solvent.
So the solvent nucleophilicity acts like a clock, determining how much rearrangement you see.
That's a great way to think about it.
And we see similar complex rearrangements in other systems, like ring contractions.
Absolutely. A classic example is the rearrangement of a cyclohexalcation to the more stable methyl cyclopentylcation. This isn't a simple 12-2 shift. It's thought to proceed through intermediates involving protonated cyclopropane structures, effectively allowing the ring to contract while migrating a methyl group. Calculations support these complex pathways.
And the examples in superacid where things rearrange multiple times.
Right, like those CRO dercations shown in scheme 4.4. In superacid, they just keep going through successive 1/3 shifts hydride methyl skeletal rearrangements until they land on the most thermodynamically stable isomer possible, often a compact, highly branched structure. In the presence of a nucleophile, the reaction would likely be intercepted much earlier.
Is there a pattern to which groups migrate best? Like migratory aptitude?
There are general trends. Aryl groups and more branched alkyl groups often migrate preferentially over hydrogen or less branched alkyl groups, partly because they can better stabilize the developing positive charge in the bridge transition state. But it's not absolute. Stereoelectronic control is also crucial. The migrating group's sigma bond must be able to align properly with the empty orbital for the shift to occur efficiently. Relief of strain can also play a major role in driving certain rearrangements.
Okay, this leads us directly into arguably one of the most famous and debated topics in physical organic chemistry, the non-classical ion problem.
Yes. Prepare for a journey into the fundamental nature of chemical bonding.
What exactly is a non-classical ion?
It challenges the traditional Lewis structure view of bonding, 2 electrons localized between 2 atoms. Non-classical ions involve the delocalization of sigma electrons and the formation of 3 center 2-electron bonds. Instead of the charge being localized on one carbon, it's shared over multiple atoms, often involving bridging by hydrogen or carbon groups through sigma bond participation.
And the poster child for this whole debate was the Norbornalcation.
Absolutely. The two-Norbornal system became the battleground for decades, pitting 2 giants of the field, Saul Winstein and H.C. Brown, against each other.
What were Winstein's key observations that started it all?
3 main things for the solvolysis of 2 Norbornal derivatives. Like the brosylate, a good leaving group. 1. Rate enhancement. The exoisomer, leaving group pointing away from the C1-C6 bridge, reacted about 350 times faster than the endoisomer, leaving group pointing towards the bridge. 2. Stereochemistry. Both the exo and endo starting materials gave exclusively the exo-substituted product. No endo product was formed. 3. Racemization. The exclusively exo product formed was always completely racemic, even if starting with optically pure reactant.
Okay, faster rate for exo, exclusive exo product, and complete racemization. How did Winstein explain this trifecta?
He proposed that the exoisomer's reactivity was enhanced because the sigma electrons of the C1-C6 bond, located on the backside of the C2 leaving group bond, directly participated in the ionization. This participation led to the formation of a symmetrical, bridged, non-classical ion intermediate.
Symmetrical and bridged.
Yes. The positive charge wasn't localized on C2, but was shared between C1, C2, and C6, with the C1-C6 bond essentially bridging over to C2. Because this proposed intermediate was symmetrical, axial, subsequent attack by a nucleophile would occur equally well at C1 or C2, which become equivalent due to the bridging, always from the exo face because the endo face is blocked by the bridge, leading to the exclusive formation of a racemic exo product.
That elegantly explains all 3 observations.
So what was H.C. Brown's objection?
Brown argued vehemently against the non-classical ion. He proposed that the observations can be explained by invoking a rapidly equilibrating pair of classical secondary carbocations.
So just 2 normal carbocations flipping back and forth really fast. Exactly. He suggested that the initially formed classical secondary carbocation at C2 underwent extremely rapid 1-Barrero-2 hydride shifts, specifically a Wagner-Meerwein shift involving the C1-C6 bond migrating, effectively moving the positive charge between C1 and C2. He argued this rapid equilibration would scramble the stereochemistry, leading to racemization. And he proposed that nucleophilic attack on this equilibrating mixture simply occurred much faster from the less hindered exo face, explaining the exclusive exo product.
So the debate boiled down to, is the bridge structure a stable intermediate, Winstein's non-classical ion, or just a transition state between 2 rapidly equilibrating classical ions? Brown's explanation.
Precisely. Is the energy profile a double well with a high barrier, Brown, or a single well representing the stable bridge ion, Winstein, potentially with small barriers leading to it? It was a fundamental question about bonding and intermediate structure.
How was this decades-long, often heated debate finally resolved?
The key came, once again, from direct observation using NMR spectroscopy in superacid media at very low temperatures. Ola and his group were able to generate the Norbornal condition under stable ion conditions.
And what did the NMR show?
The H and especially the NESC NMR spectra were definitive. They were completely inconsistent with a rapidly equilibrating mixture of two distinct classical ions. Instead, the spectra showed a high degree of symmetry, with signals corresponding to averaged environments, perfectly matching what would be expected for a single symmetrical, bridged, non-classical ion structure. The rapid equilibration hypothesis couldn't explain the observed spectra.
So Winstein was right. The non-classical ion exists as a stable species.
The evidence strongly supports the bridge structure as the minimum energy form, at least under superacid conditions. Calculations estimate this bridging provides significant stabilization somewhere between 6 and 11 kilocoulombs compared to a hypothetical classical secondary ion. Modern high-level computational studies also consistently find the bridge structure to be the most stable, and they can accurately reproduce the experimental NMR chemical shifts and even IR frequencies.
Is there a modern way to describe the bonding in this non-classical ion?
Yes, sophisticated theoretical analyses like atoms and molecules, AOIM, suggest the Nord-Bornholm ligation might be best described as a sort of complex. It involves electrostatic attraction between what resembles a protonated C1-C2 double bond and the positively charged C6 atom. This view also neatly explains why attack occurs exclusively from the exophase.
And does this bridging stabilization also happen during the actual solvolysis reaction, not just in superacid? Does it explain the rate enhancement?
Yes, the evidence suggests it does. The fact that the rate enhancement for the exoisomer becomes even more pronounced in less nucleophilic solvents, like TFA versus acetic acid, indicates that the C1-C6 bond participation is occurring in the transition state for ionization, lowering its energy. Substituent effects studies also point towards charge developing at C6 during ionization, consistent with participation. So the bridging helps the leaving group depart in the first place.
So the non-classical ion concept is real and important. Are there other examples beyond Nord-Bornholm?
Oh yes. Scheme 4.5 in the text shows several others, like the bicyclobutonium ion in ions derived from cyclopropyl systems, where sigma bond delocalization and bridging lead to unusual stability and reactivity.
Are there general rules for predicting when bridging will occur? When will a carbocation be classical versus non-classical?
Some general guidelines have emerged. 1. Tertiary cations are almost always classical. They are usually stable enough on their own that bridging doesn't offer significant additional stabilization. 2. Primary carbocations are generally too unstable to exist as classical ions. They rearrange instantly. Bridged ions often serve as transition states or intermediates in their rearrangements. The simplest carbocation, ethelium, CuH0, is actually hydrogen bridged in the gas phase because it can't rearrange to anything more stable. 3. For secondary conjugations, it's a delicate balance. Systems like Nord-Bornholm are non-classically bridged. Others, like the simple 2-propylcation, are classical. It depends heavily on the specific structure, particularly strain and the ability of sigma bonds to align for participation. 4. Bridging is generally favored when a strain bond can participate, relieving strain, or when solvation is poor, like in superacid or the gas phase, making internal stabilization more critical. Conversely, strong solvation or the presence of nearby counterions, like in ion pairs, tends to favor classical structures.
It's an incredibly rich and nuanced area, really pushing the boundaries of how we think about chemical bonds. This has been an absolutely fascinating journey through the theory mechanisms, ion pairs, carbocation stability, rearrangements, non-classical ions. But as you said at the beginning, this isn't just confined to the academic lab. These concepts have massive, real-world consequences. And petroleum processing seems like a prime example.
It's arguably one of the largest-scale applications of carbocation chemistry on the planet. Modern society runs on the products of petroleum refining gasoline, diesel, jet fuel, heating oil, plus the starting materials for plastics, pharmaceuticals, and countless other chemicals.
And refining isn't just distilling crude oil into different fractions.
Distillation is the first step, separating by boiling point. But the real chemical magic happens in subsequent processes that actively change the molecular structure of the hydrocarbons to make more valuable products. Key processes here include cracking, hydrocracking, and catalytic reforming. And carbocations are the start intermediates in most of these.
What's the main goal of these processes? Making better fuel?
Largely, yes. Especially producing high-quality gasoline with a good octane number.
Right, the octane number. Higher is better. Prevents engine knocking.
Exactly. Engine knocking, or pre-ignition, reduces power and efficiency and can damage the engine. The octane scale is based on comparing a fuel's performance to mixtures of heptane, octane number 0 knocks easily, and 2.24/4 trimethylpentane, also called isooctane. Octane number 100, very resistant to knocking.
And molecular structure makes a big difference.
Huge! Straight-chain alkanes have low octane numbers. Branching significantly increases the octane number. Isooctane itself is highly branched. Aromatic compounds also generally have high octane numbers, so refining processes aim to convert straight chains into branched chains in aromatics.
It's especially important now that lead additives are gone and MTBE is being phased out too.
Absolutely critical. Lead used to be the primary octane booster, but it's environmentally toxic. MTBE, methylbutyl ether, was a replacement, but it caused groundwater contamination issues. This has put enormous pressure on catalytic reforming and isomerization processes to produce high-octane gasoline components directly from hydrocarbons, relying heavily on carbocation chemistry.
So how are carbocations used to make, say, that isooctane standard?
A key process is the alkylation of isobutane with isobutene or other light alkenes. These are C4 hydrocarbons, often byproducts from cracking units. They are reacted together in the presence of a strong acid catalyst, like sulfuric acid or hydrofluoric acid.
And this makes C8 compounds.
Yes. The acid protonates the isobutane to form the T-butylcation. This carbocation then attacks isobutane, abstracting a hydride to form isobutane's carbocation and neutral isobutane. Or the T-butylcation can add to another molecule of isobutene, initiating a chain reaction involving further additions and crucial intermolecular hydride transfers between carbocations and alkanes. The net result is the formation of highly branched C8 alkanes, predominantly isooctane. It's a very effective way to upgrade low-value C4 streams into high-value gasoline components.
Clever use of carbocation chain reactions. What about cracking? What does that involve?
Cracking does exactly what it sounds like. It breaks down large, heavy hydrocarbon molecules, like those found in gas oil or residue fractions, which have low value as fuels, into smaller, more volatile molecules suitable for gasoline and diesel. This is usually done at high temperatures over acidic catalysts, often zeolites.
Carbocations driving the breaking of CC bonds.
Precisely. The process involves the formation of carbocation intermediates, which are prone to rearranging and, crucially, undergoing beta scission, where a CC bond breaks two carbons away from the positive charge, yielding a smaller alkene and a new, smaller carbocation. This fragmentation process continues, breaking down the large chains.
And you mentioned cracking might involve those weird pentacovalent carbonium ions.
Yes, particularly in the initiation steps or when dealing directly with alkenes. It's thought that the strong acid catalyst can actually protonate a CH or even a CC sigma bond in an alkane, forming a highly unstable, fleeting pentacoordinate intermediate like CHR or protonated propane. These species rapidly lose hydrogen or smaller alkanes to generate the more conventional trivalent carbocations, carbenium ions, that then drive the cracking and isomerization chemistry.
So cracking produces smaller alkanes and alkanes. Are other reactions happening too?
Oh yes. The alkanes produced can be alkylated by carbocations. Cyclization can occur. And under certain conditions, especially with specific catalysts like the cycler process, using gallium-modified zeolites, you can promote aromatization, converting light alkanes like propane and butane directly into valuable aromatic compounds, benzene, toluene, and xylenes, BTX, which are high-octane components and crucial chemical feedstocks.
Fascinating. What about hydrocracking? How is that different?
Hydrocracking combines cracking with hydrogenation. It's particularly useful for processing heavy, low-quality crude oils that contain a lot of sulfur and nitrogen impurities. It's typically done under high hydrogen pressure using dual-function catalysts, often a transition metal like platinum or palladium, for hydrogenation, supported on an acidic material like a zeolite for cracking and isomerization via carbocations.
So it cracks the big molecules and removes impurities and saturates alkanes simultaneously.
Exactly. It produces cleaner, more stable fuels like gasoline and diesel.
You've mentioned zeolites several times as catalysts. What are they and why are they so important here?
Zeolites are crystalline aluminosilicates. They have a porous structure with well-defined channels and cavities, almost like molecular-sized sponges. Crucially, the aluminum sites in the framework create strong Brensted acid sites, proton donors, when balanced by a proton.
So they are solid acids.
Yes, powerful solid acids. Their porous structure is key. The size and shape of the pores can control which molecules can enter and react, leading to shape selectivity. Certain zeolite structures might favor the formation of paraxylene over its ortho and meta-isomers, for example, because only the slimmer para-isomer fits neatly out of the pores.
Shape selective catalysis.
Yeah.
Very clever. And the carbocation chemistry happens inside these pores.
Yes. On the acidic sites within the zeolite channels, there's a dynamic interplay. Alkanes react with the acid sites, alkanes get protonated to carbocations, carbocations rearrange, often via those protonated cyclopropane mechanisms to get around steric constraints in the pores, undergo beta scission, alkylate other molecules, and participate in hydride transfer reactions with alkanes. It's a complex soup of carbocation reactions, all confined within the zeolite structure, ultimately leading to the desired product mixture.
It sounds like the studies of carbocations and superacids really provided the fundamental understanding needed to design and optimize these industrial zeolite catalysts.
Absolutely. Superacid studies helped elucidate the fundamental ways alkanes interact with strong acids, the mechanisms of CH and CC bond activation, fragmentation pathways, and the propensity for rearrangement and hydride transfer. This knowledge was directly transferable to understanding and modeling the much more complex reactions occurring on solid acid catalyst surfaces in refineries. Theoretical modeling of these processes, often starting from principles learned in superacid chemistry, is now a vital part of catalyst design.
It's incredible how studying these seemingly exotic, highly unstable intermediates in the lab led to technologies that underpin such a massive global industry.
It really is a testament to the power of fundamental research. Understanding the intricate dance of these fleeting carbocations allows us to control reactions on an immense scale, transforming low-value raw materials into the fuels and chemicals that power our modern lives.
What an absolutely incredible journey we've been on today, from drilling down into the fundamental SN1 and SN2 pathways,
Through unraveling the crucial subtleties of ion pairs and the whole idea of a mechanistic continuum.
then exploring the dynamic life of carbocations, their stability, their incredible tendency to rearrange, and that whole fascinating saga of non-classical ions.
And finally, connecting all that fundamental knowledge back to the massive real-world applications in petroleum refining. It really covers a vast landscape.
And it hammers home the point that this isn't just, abstract chemical theory for exams. Understanding these reaction mechanisms is absolutely essential for chemists who are designing new ways to make medicines in the lab.
Or engineers, optimizing the gigantic catalytic reactors that produce the fuels we rely on every single day. It's about seeing and controlling that intricate dance of electrons and atoms at a fundamental level.
It really makes you think differently about, almost everything chemical. When you look at a plastic bottle or fill your car with gasoline, you can start to appreciate the mind-boggling number of electron movements, fleeting intermediates, and carefully controlled carbocation reactions that had to happen to create that final product.
Absolutely. And it leads to that classic scientific question. How much more is there still to discover? Even these fundamental transformations, studied for nearly a century, still hold surprises and offer opportunities for new discoveries and better technologies. What hidden pathways and controlling factors are we still missing?
That is a fantastic thought to leave us with. Frontiers always moving. Well, a huge thank you to you, our listener, for taking this incredibly detailed deep dive with us into the world of nucleophilic substitution and carbocations.
Yes, thank you. We hope you feel you've gained a deeper understanding and appreciation for these vital chemical processes.
Keep exploring those mechanisms, keep asking those why questions, and definitely keep that scientific curiosity ignited.
Thank you for being part of our Deep Dive family. Until next time, keep diving deep.